Hello everyone, welcome to my YouTube channel. Today we will be discussing about free particle in quantum mechanics. So let's get started. What is a free particle? A particle which is free to move anywhere in the space is known as a free particle. So there is no force acting on the particle. As there is no force, so the potential energy is constant, and conventionally we choose the potential energy as 0. Schrodinger equation in one dimensional is I h cut del psi by del t minus h cut square by 2m del 2 psi by del x square v psi, where v is the potential energy, and as the potential energy is 0, so from equation 1 we can write I h cut del psi by del t equals to minus h cut square by 2m del 2 psi by del x square. This is a partial differential equation, and the best method to solve it is by separation of variable, and we are doing the same here. Let's say psi can be written as x into t, where x is only a function of x and capital T is only a function of t or time. From equation 2 we get, after putting psi equals to xt, this equation 3. Then by dividing by xt we get I h cut by t dt by dt minus h cut square by 2m into 1 by capital X d2 capital X by dx square. And as these two equations are of two different variables, the first one only depends on t or time, and the second one only depends on x or position. So to satisfy this equation, they must be equal to a constant individually, and I am considering the constant h cut omega here. So from this part, I h cut by t d capital T of dt equals to h cut omega. We solve this equation and get t equals to a1 e to the power minus I omega t, where a1 is some integration constant. Then from the second part, minus h cut square by 2m 1 by capital X d2 capital X by dx square equals to h cut omega, and taking all the parts to the right hand side of the equation and then writing 2m omega by h cut as k square, we get this form of equation, and we are very familiar with this kind of equation. The general solution is exponential type or sine cos type, but here we are considering the exponential type solution. So x equals to a2 e to the power I kx. So the total solution is x into t, and we get a e to the power I kx minus omega t, where a is a1 into a2. Similarly, for 3D case, we can get psi rt equals to a to the power I k dot r minus omega t, where k is the wave vector, r is the position vector, a is the constant. We have assumed that k square equals to 2m omega, so from there we can determine omega as h cut k square by 2m, and we know the energy is given by h cut omega. So after putting omega equals to h cut k square by 2m, we get h cut square k square by 2m, and we know that p equals to h cut k, so energy becomes p square by 2m. Here psi rt is not square integrable. We can see that this is not square integrable, psi rt. this equation is not integrable. That is, it doesn't represent a physically realizable solution. We have already discussed this in the previous lecture that psi has to be square integrable to represent a physically realizable solution. The momentum of this wave function is certain and is given by p equals to h cut k. So we can say that these are the eigenfunction corresponding to the momentum measurement. The general solution is a linear combination of all the eigenfunction. Because Schrodinger equation is linear and homogeneous, so any linear combination of solutions is also a solution of Schrodinger equation. As the free particle can have any momentum, so the linear combination will be a continuous one. We know that a free particle momentum can have any value from minus infinity to infinity. So there are infinite number of eigenfunctions, and to get a linear combination we have to take the continuous integration 1 by 2 pi to the power 3 by 2 integration of gk e to the power I k dot r minus omega t d3k, where gk is the constant of expansion. As in case of discrete we used ci, here gk plays the same role as ci, and 1 by 2 pi to the power 3 by 2, this factor is present because we want to write gk as a Fourier transform of psi rt. For 1dk, psi xt is given by 1 by root over 2 pi minus infinity to infinity gk e to the power I kx minus omega t dk. At t equals to 0, psi x0 is given by 1 by 2 pi. Just put t equals to 0 in this equation and we get gk to the power I kx dk. gk is the Fourier transform of psi x0. We can write gk as 1 by root over 2 pi minus infinity to infinity psi x0 e to the power minus I kx dx. And we are very familiar with this equation. This is the Fourier transform of the function psi x0. Actually, psi x is a wave packet, and we will learn about wave packet in the next lecture in very detail, and it represents the state of the free particle whose probability of presence or being at t equals to 0 is practically 0 outside a certain region or certain interval of width delta x, and which is centered around a particular point x0. We will learn about this in the next lecture in great details. So if gk equals to a Dirac delta function delta k minus k0, so from this equation psi x0, this equation, after putting gk as delta k minus k0, we get psi x0 as a e to the power I k naught x, where a is some constant. This is a plane wave equation and it has a well defined momentum p naught equals to h cut k naught. If we measure the momentum of the system or the particle which is in this state, we will definitely get p naught as its momentum. From this discussion we can see that e to the power ikx represent the eigenfunction corresponding to momentum p equals to h cut k. These functions are known as momentum eigenfunction, and gk's are the coefficient of expansion. As I have told you already that gk's are the coefficient of expansion and are playing the same role as ci, which is used in discrete case. Let's say dpk bar is the probability of obtaining momentum between h cut k and h cut k plus dk. So we know that the coefficient of expansion is gk square. but as this is a continuous form, so here we are using gk square dk. In case of discrete, we have used ci mod square. Changing the variable from k to p, we are just changing the variable. So psi x0 can be written as 1 by root over 2 pi h cut integration psi bar p e to the power I px by h cut dp, where gk is changed to psi bar p, where psi bar p is the wave function in the momentum space, not in the ordinary 3D space, in the momentum space. And from Parseval's theorem of Fourier analysis, we can say that mod psi x0 square dx integration equals to mod psi bar p square dp integration. Psi bar p is the wave function in momentum space, and phi, let's say phi equals to 1 by root over 2 by h cut e to the power I px by h cut. This is known as the momentum wave function. And the 1 by root over 2 pi h cut, this factor is present to fulfill the condition of dimensionality. There is nothing more than that. Only to satisfy the dimensionality we are using this factor in the beginning. If psi bar p is normalized in the momentum space, that is psi bar p square dp integration minus infinity to infinity is 1, then dp bar is probability of getting momentum between p and p plus dp, which can be written as mod psi bar p square dp. As in normal 3D space, we find the probability of getting a particle at a position r at time t is mod psi xt square dx. Similarly, in the momentum space, the probability of getting momentum between p and p plus dp is psi bar p mod square dp. And Heisenberg uncertainty relation is a very important and most debatable concept in quantum mechanics. It is very weird. Let's see what it is. It is impossible to define at a given time both the position of the particle and the momentum to an arbitrary degree of precision. And the mathematical expression is delta x delta p is greater than h equals to h cut. We will learn this in great detail in the consecutive lectures. I am just stating the statement here, and this is just the introduction of Heisenberg uncertainty principle. This is actually how the nature works. This is no experimental failure or something like that. There is no experiment that can measure position and momentum simultaneously to a great degree of precision. There must be some uncertainty which must be greater than or equals to h cut. And what is delta x, delta p? These are uncertainties in position and uncertainties momentum. Thank you very much. I will see you in the next lecture.